Good morning. It is Wednesday, the 11th of March. This is Class 20, Week 10. We're in Engineering 11, Intro to MATLAB. I have some announcements that I wanted to talk through with you today. So due today, by 12:50 p.m., and this is a hard deadline because I have a meeting that I have to go through at 1, so I need to get the heck out of this room at 12:50. So I guess this is final exam. Write your own questions. Assignment. And how many questions am I hoping for? 2 of them. Also due today is your Lab 4 papers. Report, see email. Anything else that we had for today? I think that's it, right? I do want to say you all are probably familiar with something that I'm familiar with, which is the idea that there's something called the coronavirus. I would not be surprised if we moved the next week to a take-home format. So it may be the case that our final exam is a take-home final exam. I'm okay with that. I would have you do something called sign a academic integrity pledge, that the work that you do is your work. At some point I'm going to connect with Michelle. She had this really interesting thing where you could have an app on your phone that takes physical pieces of paper and turns it into a PDF document that you can email it. So I'll ask her about that again because I wrote it down and I don't remember why. PDF, and then you could email that to me. Some people were saying that like you should physically mail it in, and that's not. I'm willing to like print out these things and then grade the print. It's not the most efficient for me. It costs a lot of money to print all the stuff, and then I have to go through like 20 emails and download everything. But I think it's way more likely that is convenient for all of us, and I could turn those around much quicker rather than like, oh, my final got lost in the mail. Oh. Yeah, right. So I don't have an answer of whether or not that's going to happen. The other thing that I wanted to talk about before we get into lecture is, and maybe we can talk about this later, the date of the final. I would really like to be able to grade the final and get it back to you before the end of next week. And so on my part, it's actually most convenient is if the final's on, assuming that the final's in class, it would be really convenient if I could get those on Monday so that I could grade it, have it back to you on Wednesday, give it back to you that day. If the final's at home, I don't have a good answer about how to get you that. I guess this is what do they call this? An exercise in learning that life is fickle, right? It is my intention to get you your graded finals back by the end of next week, and I think if it's okay with you, maybe we can be comfortable with the uncomfortable. So we'll make that decision later today when we reach critical mass as a team. Any questions before we go on about that? Yeah, Taylor. I generally take. I generally grade take-home exams at a higher expectation rate than I take in class, because in class you're limited to 3 or 4 hours, where take-home you're limited to like 4 days, right? And so the level of clarity that I expect at a take-home exam, that's something that we can talk through, though. I'm putting you on notice because I've been put on notice.
I just want to make sure.
Yeah. If it is the case. Yeah, oh, the questions would be the same level of difficulty. My expectations for your responses would go up a little bit, but I would actually give you some examples of the type of response that I would expect, and I could talk through with you what I expected and how I expected it, et cetera, so that you have access to, so that you're not confused about what it is that I'm looking for, right? And that's a conversation. This is your learning experience as much as my teaching experience, right? Okay. All right, are we ready? Okay. The next thing I want to show you, before we jump in, today we're going to do Newton's method, which is kind of a canonical, a very, very popular introductory algorithm to numerical analysis. But I wanted to show you an article that we're going to discuss today. You don't have to read this per se, but I do want to introduce it to you, and I want to show you where you could get it if you were to read it. So if we go to Introduction to Numerical Analysis, right now that's lesson 8, and then you go down to Definition of Numerical Analysis by Lloyd Trefethen. So this was written in 1992. Lloyd Trefethen is I would say, world famous numerical analyst. Is it Nick Trefethen? That's interesting. So I guess his first name is Lloyd. Here he is. He's written many books that I've studied very, very deeply. Like I solved every problem of the book. This was my PhD thesis right there. Except not via SVD. Mine was via Band Arnoldi, which is different. So anyways, he is been a really productive space. He has this very interesting definition of numerical analysis, and we're going to talk through what that definition is in the context of the work that we're doing today. But most of the ideas that I got to talk about the start of today's lecture are from this document. I've read this document probably 7 times in the last 15 years, and every time I read it, I get something new out of it. So that's there for you. All right. So we will get into the concept of Newton's method in just a moment. I wanted to focus on the following definition of something called numerical analysis. Do you all remember, I've been grading your Lab 3s, so I have some sad news. Lab 3 is taking me forever to grade because I'm reading every one of your words. Maybe you all want to laugh and say, haha, you're suffering too. I had really wanted to get you your graded Lab 3s done by Monday, and then I'd wanted to get you the graded Lab 3s done today. No matter how much time I've dedicated, it hasn't been enough. I'm working on it, and let it be known that just as you're suffering, I am suffering too. Awesome. So let me ask you this. Do you remember the article, I forget which article it was, that gave 3 different subfields of scientific computation? Do you remember what those subfields were? Many of you have written about those. One of them was algorithm development, right? Oh, I'm not talking about pillars of science. I'm talking about under scientific computation. So we had this concept of... So let's test ourselves. Scientific computation. I mean, you can look at your responses. I'd like to develop this as a team. So there was a definition. I think this is the one from SciEM, right? It was number 2. One of them was like computer infrastructure. So let me know when you got it. I'm going to let you all tell me. Okay, so this is algorithms, computer, and information science, you said? And then computer infrastructure. And I believe in computer infrastructure, that was infrastructure was like hardware and software, right? Okay. I would say there are, in algorithms, so numerical analysis is a subset of a larger development of algorithms, and we're not going to talk about this today. But one of the really interesting things about algorithms is that they depend on the hardware that you're running, right? So depending on what type of hardware you're running, you have to be conscious of that in your algorithm, and that is a major theme in the development of numerical analysis, which we'll see. So this fits into that larger conversation that we're having. MATLAB is a I professionally, as a research scholar and mathematician, I used MATLAB to prototype new algorithms in numerical analysis. So you remember the 5th article that you read by Greg Wilson talked about the idea, get an algorithm working before you optimize it? It was part of those 8 things that had like a bunch of sub things. MATLAB is designed to do this really well. So if any of you are need to or plan to take a numerical analysis class in your future, MATLAB can be a very powerful tool in that class. We are about to learn Newton's method, which is one of hundreds, if not thousands, of numerical algorithms that compose the field called numerical analysis. Before we go to that, I want to give you a sense of what we're doing here. And so I'm going to say this. Could somebody read that out loud, that definition? Yeah, for the problems of continuous mathematics. So we're going to dissect this definition. This is a very deep definition. And novel, in fact. This definition was first proposed in 1992 in that paper that you saw. Not all mathematicians working today agree on this. So the whole idea of numerical analysis is that we design and study algorithms that solve continuous problems. Does anybody see an issue with the idea of continuity and the concepts that we've played with in this class? Yeah, that is a sub-theme of the concept of numerical analysis. Yep. Okay. So, when working as a numerical analyst, one of the major ideas, one of the things that we design heavily is the idea of devising algorithms to solve specific applied problems in science and engineering. So the idea on that is that how many of you were pretty amazed at how much work and thought you had to have to even graph a solution to the pendulum problem? Okay. Did you notice the theme that you actually had to have knowledge, field-specific knowledge about the problem to say anything intelligent in graphing the damn thing? Okay. that assumes that you had, when you graphed them, you had access. So anybody use the cosine curve? How did you know the cosine curve works? Imagine that there was no such thing as a cosine function, and you had to, what do we know that MATLAB knows how to do? Addition and subtraction, multiplication and division. So guess what? If we were in the 1940s, guess what we would have done instead of graphing the cosine? We would have devised an algorithm to combine data types with addition, subtraction, multiplication, and division to be able to create something called a cosine function. That's exactly what the MATLAB people did. So when you call cosine, in the back of that, there's an entire algorithm that uses IEEE 754 format, addition, subtraction, multiplication, division, to produce numerical approximations to the output of the cosine function at the input that you've determined. The people that wrote that code are called numerical analysts. So I did want to talk about this today because many of you, when I first met you, did something that I absolutely loved, which was that you were very skeptical of me, right? This is a MATLAB code class. I need to know how to code syntax in MATLAB. What the fuck is this guy doing? Thank you. I love that skepticism. It's good to have that. Don't trust your teachers ever. I've now heard from many of you that are kind of happy. And I don't know if all of you are happy, but I've heard many people give me positive feedback like, oh, okay, I'm really happy I went through this. I wanted to tell you though, so what's the whole idea of numerical analysis? What does the study of numerical analysis do? Study algorithms, study and make algorithms to solve problems in continuous mathematics. Could you guess why we care about continuous mathematics? Let me ask you this. That problem, discrete or continuous? Continuous. Why do we care about continuity? Yeah. The world around us is continuous, right? Not really if you get down to the quantum level of that, but we can model it via continuity, right? Okay, so what's numerical analysis again when we think about it? Study of... Yeah, algorithms for continuous problems. The first part of that study, I'm going to claim, is to devise algorithms, and then this is where students usually get some new information. If you devise algorithms that solves applied problems that people want to solve, it's much more likely that you'll earn a paycheck, right? You can divide out, like, so for example, Jean, if you ever talk to him, Foothill College, I don't know if they're paying for that, are they? Yeah, they pay. So he's actually, I don't know if I would call you a numerical analyst because I think you're borrowing other people's algorithms, right? But from the standpoint, you are definitely in the field of numerical analysis-esque type of work. If you want to talk to him about what he's doing right now, he's got a great applied problem that Foothill College wants to pay for, and I hope they're paying you. Yeah, so you're making money devising algorithms right now. Awesome. Okay, so first part of that study is to divide algorithms. The second thing that I'm going to say, and this is why I'm so serious about teaching the class that I teach in this way, this line right here. When we're devising algorithms to solve problems, one of the things that we want to make sure is that the way that we solve the problem actually solves the problem that we want to solve. You ever get an answer to a math problem and you're not sure if the answer is correct? Okay, do you know what most students do when they get an answer to a math problem and they're like, I don't know if it's correct? Look for an answer key or submit it and pray, and then they let the teacher decide whether or not it's correct, right? Okay, here's a crazy reality. In numerical analysis, and especially in the early days, there was no teacher that could tell you whether or not shit had been done right because nobody had ever done it. So one of the fundamental pieces of developing algorithms is not only the idea of devising it, but after you've initially proposed, hey, this is what I think is going to solve the problem, can you guess what you need to check? Does the code that I produce actually solve the problem that I think I'm going to solve? And that's where something called analysis of algorithms comes in. Here is a really, really sad fact. Okay, you all have your first numerical analysis algorithm, at least in your mind. You haven't learned how to develop that on a breadboard yet. But what if I asked you to do this? Okay, question. What type of object is that? Continuous or discrete? Well, it depends on what system you're in. If you're in base 7, I agree with that statement. That wasn't funny? Oh, come on, that was a little funny. Here's another question. This is a continuous problem. Why is that a continuous problem? What is continuity? Think about Math 1A. What is the difference between Math 1A and Math 48A, B, and C? And Math 105 and Math 228 this class. What's the difference between calculus and algebra? Limits. This problem is a limit problem. What do I mean by that? In order to get that value in the computer, I need to take a limit. The same thing is true here, to be honest with you. We actually saw, I think we actually did the geometric series expansion of something over 10. Do you remember that? Okay, so here's the claim. This is a problem in continuous mathematics because in base 2, it requires limits. Limits are the definition of continuity. What did we notice in IEEE format when we actually went to implement this on a computer? Okay, here's a claim. The algorithm we're going to use to implement this is a conversion algorithm from this set of strings into the IEEE 754 format. We didn't develop that algorithm for ourselves, though if we had, we would have won the equivalent of a Nobel Prize. Think about that. You all now have an intellectual understanding of material that won somebody the Nobel Prize. Turing Prize, I'm sorry. Yeah, you can look that up on your own. Okay, so here's a claim. This is continuous. We have an algorithm to translate this into a data structure on the computer. What do you notice the moment we try to implement this on a computer? Josh has already said it. What happens? It's discrete, and we actually don't capture it immediately. And so the moment that happens, the question that we have is, does our algorithm produce the solution that we expect? Well, formally speaking, if we're stuck in the concept of continuity, what do we expect from this? We expect that the number that we store is exact. We have an algorithm that stores a non-exact number. If we implement the expectation that we store it exactly, does our algorithm solve that problem? Nope. So can you guess the immediate next question that a mathematician might ask herself? Well, how bad is it? Right? And that's called error analysis. Here is, so we'll get into that. We're going to get into, these are major themes. If you go on in numerical analysis, you're going to see this for days. You can come back. I post my lecture notes online. That paper is posted online. You can return back to this. But I do want to expose you to these ideas. So I wanted to talk about this concept. Continuous mathematics is the idea that many of the ways that you think about these in math will require real numbers. I'm not talking about the solutions to them. I'm talking about how we describe those. Has anybody taken Math 2A? that concept is ordinary differential equations. There's also something called partial differential equations. Partial differential equations, ordinary differential equations is to partial differential equations what Math 1A is to Math 1C. What's the difference between Math 1A and Math 1C? 1A is single variable, Math 1C is multivariable. Ordinary differential equations are differential equations involving a single function, single variable function. Could you guess what partial differential equations are? Multivariable functions. I don't think we've done this quarter. Finite element analysis, truss system. Have we done this already? Navier-Stokes equation, plane flight. That's a nice one. I don't know if this was made in MATLAB. Guess what you're looking at right there? These are, yeah, there's a partial differential equation. Have you ever looked at a car that's driving on the road during the rain? Have you ever looked not at the car itself, but right behind it? Next time you're driving on, don't get in an accident. No accidents. You can't, when the cop asks you what happened, you can't be, my math teacher told me to look at the back of the car, right? This is his address, go arrest him, right? Don't do that. Look at the back of the car when you're driving, because the water on the road will kick up into the air and it will allow you to visualize in live time what's happening with the air behind the car. The only reason you can't see on a day-to-day basis is because we can't see air, right? This is a numerical approximation of the behavior of air molecules flowing over a car traveling at some certain speed. In the back, this is called turbulence or chaos dynamics, depending on how you look at it. The designers of this car spend a ton of time thinking about how these forces interact. And then, do you see this little like orange and red part? I'm not sure what U magnitude is. This is basically a numerical solution to something called Navier-Stokes equation. For you to understand how they coded up, you would need at least, I would imagine, 5 years of very, very deep studying from where you are today to even understand the start of that code. But here's the idea. Car driving down the road, wind passing, continuous or discrete? Continuous. The equation that governs how the air passes over the car is called Navier-Stokes. The computer scientists that programmed this translated that equation into a sequence of numerical algorithms that propagate down to the core of this computer and run on IEEE 754 format, including addition, multiplication, division, and subtraction. And I think at this point square roots are actually coded into hardware. I think that's true. Does anybody know that answer? I think that's true. Right? I mean, you could, yeah, this is a really nice one. You know how long that single diagram took to produce? I would say years. The people that worked on that particular diagram probably spent years on it. It's another one. Give me some of the names of stuff that you want to get paid to do in the future. Give me some names of fields that you want to get into. Climate science? Okay. These differential equations are crazy. Yeah. Gradients, here's some gradient stuff. What other type? We got chemists. These ones are a lot less exciting. You know p orbitals? Those are inferred solutions to Schrodinger's equations. Schrodinger's equations are eigenvalue. Yeah, I'll stop. The reason that I want to, I mean, we can just go on forever. Wait, I mean, you name the thing that you look at, and I'll name the numerical algorithms that were used to design it. Let me repeat this. Our education system will not have you go through MATLAB classes formally most of the time. But when you go through your life, behind almost everything that you see that was designed, there are numerical analysts that tested that prior to manufacturing. You could ignore MATLAB just like you can avoid eating vegetables, right? Wouldn't it be nice to work on a team and make, I don't know how much money, not too much, maybe between 60 and 150 for starting? That helps analyze this? What type of skills would you need to do? The reason that I want to talk about this today is I have 2 more days with you. Do you think I'm going to be able to teach you everything you need to know in this space? There's no way in hell. But if I can start getting you thinking about, like, holy shit, almost everything I look at on a day-to-day basis, there are people in the background that use this software and others like it to prototype, analyze, iterate, refine, manufacture, and produce, and then start thinking about what would it take for me in the realms that I want to get to that. How do I reverse engineer my classes so that I can design opportunities to learn like that into my class? This directly relates to today's content in lecture because many of these concepts, these are the problems in applied math. So if we go back to this definition, what is the study of numerical analysis? Study of algorithms to solve problems of continuous math. Okay, so let me ask you this. Let's do these specific cases. Each of you who has a career goal, I'm going to claim there are continuous problems in that space. Okay, what is this problem? Name the continuous problem right here. What's that problem? When wind passes through a turbine, what type of forces are felt on that turbine? Continuous problem. Should we do one that's more aligned with my children? Yeah. I hope I'm taking your breath away. Some of you look less than enthused right now. I can't believe that. What's this continuous problem? When a crane lifts stuff and moves it, what happens? Who cares about that type of problem? The company that builds cranes. Oh, yeah. Okay. I mean, you name the thing. The fact of the matter is they're all continuous problems. What type of company would pay you? Forget about other people. If you knew how to code up this code, what type of company would pay you, and where would they get their money? What type of company would pay me 5 years to do this analysis? The companies that manufacture cranes. Why would they want me to do this? Could you guess how much it is to cost to build a freaking crane? How much is it to build a crane? 100,000s, no way. Millions. How much is it to pay me as a coder to work for a few years? A few cups of coffee, rent. If you could pay me for 5 years, me and a team of coders, maybe this group right here, for 5 years to give you a really accurate digital model of everything going on the crane at a deep mathematical level, and we could pretty much guarantee to the best of our ability that the design of the crane that we're proposing is not going to break under the type of weights, and give you specification and give you this stuff, and that costs you $1 million. Would that be worth the initial upfront cost? Why?
Because if the crane fails, it's that $1 million lost in production of the crane, plus whatever the insurance.
It's called due diligence, right?
Plus,
Okay.
specific finance.
So then the question is, what would it take? And then where would the company get the money? Well, they would just put that planning into whatever financial structure they have, right? So if they're on venture capitalist money, they would just say, we need to pay these people. There's no way around it. If they're if they're already in the market, they would just budget that as an expense, because the company wouldn't exist without the engineers and scientists that run the damn thing, right? Wouldn't it be nice to be one of the people that makes a paycheck on that? Okay, so if I'm going to get to that space, what do I pretty much, I'm not claiming you got to make this decision for yourself, but if I'm going to get to a space where I can code this up, what are some of the things I need to make in my decisions about what to learn? Got to learn physics, but it's more than just physics. If I take here's a question for you. Anybody take physics classes? Can you code that up for me? Why not? What happens in most of your physics classes? They don't teach you how to code. This is why I want to teach you how to code and teach yourself how to code. And to say, it is up to you individually, it is up to us individually to design an education that includes this if you want to be part of the cut of this money. Our education system does not require this for most scientists. That's why I wanted to expose you to the reading. That problem is endemic. However, if you're on the inside of that knowledge, what can you do individually when you develop your plans? Seek out opportunities to build into your educational plan, opportunities to learn how to code. MATLAB is a really good language to do that in. Not the best they probably have their own custom language. I would imagine there's a software company that makes millions of dollars a year whose job is to produce numerical simulations of cranes. Just cranes. We can get the name of that software, right? Yeah. So I'm going to shut up on that, and we're going to move back here. But what I want to tell you is this definition is not academic. It is academic in some sense, but it's alive in everything that you see around in your daily life. Okay. So whole idea is continuous mathematics. Can we capture continuous mathematics in discrete computers? Can we capture infinite amount of information on a digital computer like this? No. So one of the immediate questions that we have is, if we have a continuous variable x and we have a discrete approximation to x, one of the questions that we will immediately ask ourselves, first things we realize is, everything we produce on a computer will fail. If I want to approximate pi, which means I want to do something about a circle, the moment I try to do that, I have a failure. So one of the questions that I ask myself as a numerical analyst is, well, how badly did I fail? Is it good enough to say that the approximation accurately represents the idea underneath to the extent of the precision on my computer, right? So with that in mind, this is one of the themes that we're saying today. in the concept of numerical analysis, one of the things that I like to think a lot about is the idea that we are applying it to science and technology problems. Your science classes are designed to give you exposure to many of the ideas that you will need to understand the background knowledge behind the equations that you then code up in a numerical analyst package, right? The concept of applied also deals with the concept of economics. Built into the background of this, one of the questions that I always ask is, math is privilege. Who's going to pay you to spend time thinking about these ideas? And that's where the applied comes in. Yeah. Anybody ever seen Harry Potter? What do they do with those things? Say it again? It's a wand, right? What do they do with it? They're like magic, right? Okay. Here's a fun magic spell that I've thought a lot about. Imagine I had a wand that right now I could break every numerical analysis algorithm that works in the world by doing this. If that reality happened right now at this moment and I went, you know what happened? The live stream would stop. Planes would fall out of the air immediately. Cars would crash. Water systems would break down. Gas systems would break down. Telephone communications would completely go offline. Say that back to me in a way that makes sense. What am I saying right now about the concept of numerical analysis? If I had a wand that could break numerical analysis at this exact moment, I go like this. What does that tell you about the prevalence and importance of numerical analysis? That is why they said scientific computation is a third pillar. So I'm going to skip some of this. I can't say enough about this. This is one of the only spaces that I have to talk about how important this is and how poorly our educational structure is. And in 12 weeks, I can't get there. Do you hear me selling you on an idea? What idea am I selling you on right now? Find ways to get educated about this. And the reason that I want to say this now is your future institutions won't say this if they were like the ones I went to. They assume that you have inside knowledge to seek this out and that you look at a list of classes that they tell you are required and then you figure it out. And guess what happens if you don't have that knowledge and you don't act on it? Guess whose problem they say that is? Not our problem. So, there's more on this here. I will say that my MATLAB website will be running until I die, assuming that I continue to have a paycheck and I can pay the $180 a month. That thing will be updated as often as I teach MATLAB. So if you ever wanted to come back, all those resources I plan to have up there. You could also download them on your computer. I did want to talk about this concept. One of the fundamental concepts in continuous algorithms to solve continuous problems is the concept of approximating unknown values. The IEEE 754 format was our first approximation. What we're now going to do is build approximation on top of that data structure. Did my computer just... Oh, there it is. One of the sub-themes of numerical analysis, and it's actually how we put our stamps of validation, the words are accuracy and stability. So what I mean by that, there's a famous, very, very famous book. This is a postgraduate level book. You would have to have your PhD. One page of that would take me at this point in my life probably 7 to 10 hours to read and fully understand, which means it would take you to read the first page of numerical analysis on that probably 3-4 years. That book is a very powerful book. It is a seminal book in the field because, do you remember we said this idea that if we're solving applied problems with an algorithm, we want to make sure that the algorithm that we use solves the problem well? Approximations matter in that space, and so one of the questions that numerical analysts ask ourselves immediately is, how good does my algorithm actually solve my problem? So how accurate are my results? And how stable are my results? The idea of stability is the following. If I perturb my input just a little bit, so if I take I know a given input, so if I have a crane, could you guess what input I'm going to put in to the crane problem? What thing drives the type of forces? Masses, perhaps some of the other input are like wind forces, shear forces, gravity, right? Gravity, pretty constant, but it would be interesting if crane like turned around and the gravitational force changed. So here's a major problem in numerical analysis. If I change the values of my input, how does that change propagate through my algorithms? So what does that change actually do to the type of computations? There are places where small changes to inputs, so changing an input from 100 kilograms to 200 kilograms, fundamentally breaks a numerical analysis algorithm. Meaning to say the output of the algorithm is complete numerical nonsense. It tells you nothing useful. There are engineers who haven't recognized that and have built structures on faulty analysis, and then their structures collapse. Do you remember the bridge collapse that killed a few people a few years back? Tons of concrete just came down in the middle of the day. That was faulty planning. Same thing true of the Millennium Tower. Tilting in, or the footbridge. You've seen these footbridges? The concept of accuracy and stability are going down deep into the algorithm, analyzing the type of errors that you expect, and making sure that when you say, hey, my algorithm solves this problem, that the algorithm that you're proposing is actually stable enough to solve it across the type of input that you expect. This is one of the reasons when I expose you to these ideas in MATLAB at a very young age, I want to start with the deep down levels, because from that standpoint, you can actually build up a complete approach to that. So today we are going to talk about your first numerical analysis algorithm, and it is this exact one. I hope you laugh. Question, you think you can build a crane on this problem?
With enough steps, yes.
Yeah, that's the interesting thing about it, right? The funny thing is that at the end of the day, all those crazy algorithms map back to stuff that's this easy.
Yeah.
I hope that's humbling for you.
X equals X plus Y, you can build a crane on top of that
With enough steps and training and team members. So what is this problem? Tell me what the continuous part of this problem is. Okay, so forget this for a second. You're not used to, I don't think we teach you very well to think about what a problem is, right? We teach you to use math technology. What's this thing called over here? Function, all right. And then what function is this? Square root. Where's the continuous, so we're claiming that numerical analysis is the study of algorithms to solve continuous problems. Claim, there's continuity happening here. Where is it? He's so fast. What do you mean by that? Okay, so yeah, so if you put in pi, is there such thing as a square root of pi? That's a continuous problem. Where's the next part of the continuity problem? Question. The number 2, is the number 2 continuous with respect to calculus or with respect to the concept of IEEE format? Nope. 2, do you need a limit to say the number 2? Nope. And yet, here's the deal. If I put the number 2 inside the input to this problem, guess what happens? The exact output is continuous, meaning that if I go to approximate the square root of 2 on a computer, what's going to happen?
It's not going to be correct.
Can't do it. Exactly. Get it? Can't do it exactly and exactly. So here's the deal. This is going to be, this model that I have right now is actually a model for all numerical analysis. So today we're going to learn how do you take a function that has continuous output and get a good numerical approximation for the value that that output should be without actually getting the exact value. So you've seen me do this in, those of you that have taken my Math 1C and Math 2B classes have seen me do this. In fact, I put this on the Applied Linear Algebra website. That's this thing, right? So we're going to start with an input called x. What we really want to do in this problem is take the square root of x, right? So square root of 2, we want to do that. But the problem is we're going to do that on an electronic computer, right? So what do we know about the ability to go from x to its square root? Exactly. Will I ever solve that problem exactly on a finite computation machine? Nope. So first of all, there's no way to do this easily. Here's the second question. Shut all your computers, put away your pen, I'm not serious right now, put away your pens and your etc. I'm going to lock you in a room and ask you to approximate the square root of 2 to 16 digits of accuracy by yourself using nothing other than a pen and paper. And you have an hour to do it. How many of you are overwhelmed by that problem? Me too. Here's the deal though. There's another obstacle, right? We don't actually know how to compute the square root by ourselves because we've assumed all this time that every tool that we use does it well, right? Numerical Analysis says, no problem. Give me a breadboard, some resistors and transistors. After a few years, I'll produce something that does it for any number, and it will do it to any level of accuracy that you expect. Oh yeah, and I'd like you to pay my rent while I'm doing it. Right? So from that standpoint, one of the first things that we do is we approximate our input on a digital computer. So we take the original input that we had and we approximate it as, what's the premier data class for numerical analysts? IEEE 754, 64 bits, double. So now all of a sudden we take the original 2 that we've done and we write it as a computer object, x hat. What does this mean? Nobody on earth, when you go to your other instructors and say, hey, is that a type 1 number? They're going to be like, what the fuck are you talking about? Right? It has a finite, because that's literally Jeff Anderson knowledge, right? Yeah, someday maybe if I become like a leader in educational space for numerical analysis, people will realize like, oh, that's a good thing for students to know, right? They should do that. I'm working on it. So this isn't a type 1 approximation, and then what we're going to do is we're going to have an algorithm that takes that input, that numerical input, and approximates square root of the numerical input. So we're not going to take the square root of 2, we're going to take the square root of the IEEE 754 double number that approximates 2, right? And we'll produce a output which is called the square root of the IEEE number 2. And then what do we expect? If we've done our work well, if our algorithm is designed well, what do we expect about the actual value versus the computed value? Within the tolerance that we expect. And that part is well beyond what we're going to talk about in this class. That actually, you would have to be honest with you, You probably have to take 3 numerical analysis class at the upper division level and a few graduate level ones to do this for most of the problems that you would have to see. Okay. I think I've been talking at you for a while. Should we take a break? Question: how many of you, should I do this lecture again? It's not a heavy content lecture in the sense that I'm not actually expecting you to do this. I really like doing this for students because this may be the only time that you have somebody break it down in terms of your life. Do you know what most mathematicians I've ever been exposed to do on the first day in a numerical analysis class? They start solving problems that are very, very deep in numerical analysis without ever talking about the question, why is this important? Because they assume you already know why it's important and you see how it applies to your life. How many of you would recommend that in my future classes I do this type of content? Okay, so don't, in other words, when I make YouTube videos, actually make YouTube videos on the idea of why the hell this matters. At the start of the quarter.
Yeah, because some people will.
Then less people will be like, what the fuck is this guy doing?
They'll be more informed.
So,
So we can kind of confuse everybody again. You start talking about like type 1, type 2 numbers.
well, the nice thing is once the videos are made, I can put them anywhere, right? Yeah. Okay, so but you're telling me don't give up on that. Okay, it's now 10:01. Can we be back at 10:11? All right, we'll see you back at 10:11, and we'll start doing real math. Yeah, I think this is